back into the blue. And I guarantee you, every student in this class would say, Professor, if it's like the blue, I can do it. I see what that negative sign means to do, that plus sign inside means to do. I see what the green there meant to do, vertical shift. If it's written like that, I can do it. I can see the shifts and the reflections and so forth. But Professor, if you give it to me like this, I couldn't even tell. As an instructor, is this thing being shifted to the left or to the right? Well, we've already discovered it's shifted to the left. I can't tell that from here. Can you? No. And then this says it should be, what, reflected through the what? X-axis, flipped over? You might be able to tell that because there's a negative sign in front. And then all of a sudden it's what, vertically shifted down what, 4? I don't know whether you can even see that from here. So guys, I need some help, and I'll erase this. I'm jumping ahead of myself. I think this is section 2.3, maybe 2.4, where they finally ask you to do this. But I thought, no, why not do it right now? Can anyone help me change this back into this? And you'll have to use completion of the square. Can anyone tell me something about completion of the square, since we just did it on the exam? What should I be aware of if I want to use completion of the square?
Get rid of the negative.
Right here. That leading coefficient should be a what?
1.
1. Can I make it a 1? Yes. Divide or multiply both sides by what? A negative. I can quickly say, Professor, rewrite it like this. Everyone agree? By the way, is my leading coefficient now positive? It's got to be. And it's got to be a what? Positive 1. And that's the first restriction of completion of the square. Now, since you said on the exam, I need to determine with your help, I'm going to move the 8 over out of the way to the other side and add, here we go, those blanks. I've been using blanks here in my presentation. Those blanks and trying to determine what on earth, hang on, I don't want to erase anything there, must I add to complete it. That's what we did on the exam, I think. Is that true, guys? Now, does anyone remember, since we just had one of these on the exam, how does one determine what is required here? Yes?
It's going to be 4.
It's going to be 4, why?
We need to take b and
divide by 2
and square.
and then square it. Same process. So we'll take 4 and divide by 2, which is 2, and he's telling me to square it. It's a 4 on each side. This is completion of the square. Oh, way on the left, not too bad here. It's negative y minus 4. I'll put these two together. The other side should be a nice perfect square with his help, and it looks like it is. It's x plus 2 squared. It's all the right-hand side, all this. Is that the same as x plus 2 squared? That's what I wanted. Now when we get the y by itself, because the y was by itself in the blue, let's get the y by itself. Let's move the 4 over. Add it. Now the 4 has been moved over. And what would you suggest finally to get the y completely by itself? I've got a negative y. What would you suggest at this point? Multiply or divide by what? Negative? And you do, you end up with y is equal to negative x plus 2 squared and minus 4 if you multiply or divide by negative all the way through. Please tell me, is that what I originally had in the blue? Was that the original blue?
Yes.
All right, there it shows me now if I want to create something with a transformation, I can go through completion of the square and put it in the form that I need. And we're done. So it does work out. Again, guys, I'm way ahead of myself. I think this is section 2.4, but why not? Since I did here, why not show you can transform by using this also? Now, I'm going to leave that there for a while. Billy, do me a favor. Tell me on that handout, what's another transformation strategy? I stopped at reflection. What's number 4?
Horizontal stretching and shrinking of graphs.
Oh, wait, stretch. you a shrink of the graph. Now, be very careful, guys, here, gotta be very careful myself here. Now, read that to us, Billy.
It's a graph FC times X.
C times f of x?
I mean, F of C times X. So
Oh,
like CX.
F of CX.
oh, f, I got you, f of cx.
Okay, so
There you go.
C is greater than one.
Whoa, they give a restriction on this. C must be greater than one?
Shrink the graph of y equals f of x horizontally by a factor of one divided by c.
Okay, shrink the graph by a factor of 1 over c. Wow. You open up your math textbook and you read that, try to make sense of it? We're gonna try to make sense of it. Now, was there another part besides that?
Yes.
Tell me the other one.
It's a graph f of cx. 0 is less than c.
Oh, hang on now, f of cx again,
Yeah.
but this time the restriction on c is? Come between 0 and 1?
Is less than c,
Uh-huh,
less than 1.
thank you. And what happens now?
Stretch the graph of y equals f of x horizontally by a factor of 1 divided by c.
Oh, my lord. Stretch the graph, and I think you said horizontal, by a factor of what?
1 over c.
Now, this particular transformation, that's why I held off on it, will drive you nuts. If you're not careful. You gotta see me do something with it, try to make some sense of it. Billy, was that all of that particular one?
Yeah.
Now, was there another different type of transformation listed on the handout or not?
No.
Whew. There are others. I just did not list them yet. This one, I saved it, because this will absolutely drive you nuts here, and I think, let's see if I did, I brought in a graph. Guys, let me see if this is gonna work for me. Oh, let's hope so. I'm gonna give you a graph. It's not one of the parent graphs. I'm gonna give you a graph to try to illustrate what she just read to me here. And, good, I can see it right here. Here's the graph, guys. Rough sketch, I think it will make sense. The X and the Y. Now, it looks like, and I gotta look and see what I did here, -4 down 2. Down 2, and I'll put that here, is marked right here. -4 down 2. Also looks like I have 0 up to right here, marked, labeled. Then I threw in something else, I did, out 2 up to. Yeah. Right here. And my last point is 4, 0. Squeeze that in right here. And step to the side, make sure you guys have those points. -4 down 2, 0, 2, 2, 2, 4, 0. I just plot some points. I'm gonna connect them best I can. So guys, it looks like what I wanted when I created this problem was these two connected. Horizontal strip here. And then a piece that connects these two. Now from where you're seated, can you see that clearly? Whew. Now let's try something. That's my graph. I'd like to try, and it looks like right here, gotta find where I am. Yes, I'd like to see what she read to me. Hang on just a second. Yes, this is my function. This is the graph of my function. I'd like to sketch on the same grid with your help. I will sketch it in blue. I'd like to know what this might look like. Sketch, let's call it, I guess h of x is equal to this. There's my f of x in the brown or black color there. And in the blue, on the same grid, I like to graph f of 2x. Now, looking back, you gotta know these transformations. Billy, you're saying f of 2x, I've chosen c to be a 2. Right here, that's my number I chose for my example, 2. Is 2 greater than 1?
Yes.
So does it fit that first piece there she read to me?
Yes.
So she says, Ramsey, if you do this correctly, that graph that you have right now should shrink horizontally. In other words, when I finish up, it goes from here to here now horizontally. Now, when I finish up, if I do it correctly, it should close in, shrink. Now, she says to get that effect of it shrinking horizontally, side to side, there's a factor of 1 over c. Now, what was my c value again?
2.
So my 1 over c that I need to work with is what? 1 over 2. Now, can someone cleverly tell me, we'll do it in blue here, what should I do at each one of these 4 points with that 1 over 2, and then I'll connect and see if my final graph in blue has been squeezed in horizontally compared to what you see right now. What should I do to get that effect? Anyone? Yes.
Divide each of the x values by 2.
Thank you. Or multiply each one by 1/2. That's where that 1/2 comes in. Love that. Thank you so much. She's away, Professor. Billy's already given this strength by graph factor of 1 over c. You chose for your example, c is 2. Right here it is. So go through it, multiply all of the x coordinates. We're doing it horizontally, so x. Multiply all the x coordinates by 1/2. 1 over c, or she says divide by 2, either way. How about the y coordinate? What should I do with the y coordinate? Nothing. So in other words, let's start from the left here. So if I do as just suggested here, this point was -4, -2. Where is it now? -2, -2. Take 1/2 of that x, 1/2 of the -4, now changes it to a -2, and you leave the other -2, which is the y coordinate, you leave that just like it is. So guys, if I plot on this rough sketch, -2 down 2, and my, maybe somewhere in here. I'm on top of the board there. Did you guys agree? My next point was up here. 0, 2. Where is it? Where is it now in my transformation? Wait, multiply the x coordinate by 1/2. Well, my x coordinate is 0. What's 1/2 times 0? Is it 0?
Yeah.
This point stays where it is. Yes or no? My next point was 2, 2. Where is it now if I use that 1 over 2, 1/2 on the x coordinate, which is a 2? 1, 2. So move out 1 up 2. We're in here somewhere. And my last one over there is 4, 0. It now becomes 2, 0. Connect. I'm doing all this free-handed tonight, guys. Connect those. Connect this in the blue. Connect these. Please tell me, does that little blue shape, at least in terms of appearance, does it look like its parent, the larger graph I had originally? That's been what? Squeezed in. The truth? It's been horizontally, she gave me the description here was shrink. It's been shrunk horizontally by a factor of 1 over c. Yes?
What happens if c is negative?
Beautiful, hang on. I got you. We haven't discussed that one yet. Now, I'd like to, here we go, Billy. I'm gonna try this one in green. And I gotta be careful of this one myself also. I'm gonna try to squeeze the green one in on the same graph if I can, not mess it up. let's say G of X, like what students are asking us, and professor, suppose inside here is negative. So that's a different story. So hold on. Okay, G of X is equal to, guys, let's try this. F of 1/2 X. And I'll do this in green on the same grid. Now keep in mind, the original graph was the one in brown there. 1/2, Billy says if it looks like this, which it does, my C in this case, does my C fall between 0 and 1? I'm using 1/2. So if it does, by this transformation, I'm supposed to now stretch the graph by a factor of 1/C. Now, what does that mean to do? You're going to multiply the x coordinates this time by 2. 1/C, and my C in this case is 1/2. And guys, if you place 1 over down here, 1 over 1/2, is that the same as 2? So I'm supposed to multiply all the x coordinates by 2. Now watch me mess this one up on the green here. My first x coordinate is -4. Oh my goodness. If I multiply it by what, 2? Yes or no?
Yes.
Okay, -5, -6, -7, -8. Is it now over at -8? For the green, I'm going to do here. Is it -8 down 2? Don't let me mess up, because I'm right on top of the board here, trying to line these things up the best I can. Is that now there? Okay, let me label this. I think I didn't label the blue one, I'll just leave it like that. Next point on my parent graph was up here, 0, 2. Is that point going to stay there? If I multiply the x coordinate by 2, is that point 2 times 0 is 0? It's going to stay right where it is. My next point on the original graph was 2, 2. Multiply the x coordinate by 2, it's now where? 4, 2. It's out here. And my last point, I guess, was 4, 0. Where is it now? 8, 0. That's exactly what she read to me. Let's do this, stretch it out. 4, 5, 6, 7, 8. Guys, we say it's out here for a rough sketch. And you guys are saying, Professor, that's 8, 0. Yes or no?
Yes.
Connect the best I can. Free-handed, looks like that. It goes out to here, and then over to here. Please tell me, does it still resemble the original first graph I placed? Except it's been what? Horizontally stretched. Not shrunk this time, stretched. And I used exactly what Billy said to do to get that effect. Now, beautiful. The guys in the back are saying, Professor, what if there's a negative sign in front? Or not in front, inside. Okay, let's do this right now. I'm all over the board here, guys. Bear with me, I'm more race over this. They're asking this. Suppose you want the graph, and the negative sign is inside. Billy, tell me, I had no more transformations listed on that handout. Did I? This one's not listed. You gave me, I may have erased it, or did I erase it? You gave me, oh, okay, beautiful. You gave me, oh, down here. She gave it to me. If the negative sign is inside, and you haven't seen yet an example of it, but if the negative sign's inside, what does that mean to do? She says it means to do what? Reflect it through the y-axis. Okay, let's do an example. Let's say the graph, now looks like this. I'll make it very, very brief, and then we'll move on. You guys have done a good job on this. So -2, point here. Then you go up to 4. I'm just creating this right quickly. And why not? Let's go out to 5 here. Connect. quick illustration. It looks something like that, which is what passes the vertical line test. Now that's my original graph of functions. Now Theo, help me out here, Mr. Mathematician. If it says a negative sign inside, which is what these guys are concerned about, the negative sign out front, I think somewhere I did one, or did I? Did I do one where the graph flipped over? Earlier, I did, didn't I? We had a parabola and then flipped over. Oh, right here it is. Right? Now suppose the negative sign's not out front, it's inside. Can anyone tell me, based on this, what should I do to see the effect of a negative sign inside? And then we'll be finished with all the major transformations. Okay, that's the description. It's a reflection through the y-axis. And Billy, I think you told me that even on the handout. Now, what does that mean I should do to these 3 points to make that happen? To show that this graph is now going to be reflected across the y-axis, and we know where the y-axis is, right here. Not the x, so it's not going to be one of these. It's flipped over. It's going to be reflected through the y-axis. Can anyone tell me what should I do with those 3 points to try to get that effect? F of a negative x.
Multiply the x values by -1.
I heard multiply the x values by -1. Let's see what happens. Billy, I'm going to put this in green. My first x value, I better be careful here myself. This was -2, 0. This is 0, 4. And I made it fairly easy here. This is 5, 0. So she's telling me, Professor, multiply all the x coordinates by negative. If I do, this now becomes what? Positive 2, 0. So it's now here in the green. My next point is 0, 4. If I multiply the x coordinate by what she wants me to do here, by what? A negative? Well, let's stay right where it is. Yes or no?
Yes.
And the last one, I guess, was 5, 0. It now becomes what? Negative 5, 0. So this stretches out to a -5. And see if this is making a little sense here. So now I'm not here. And here's where we think it should be. Wow. You guys think it's going to be correct? If I go through and multiply all the x coordinates by negative, or -1. Did I do it correctly? If I connect, am I connecting from here to here, then down to here, or not?
Yes.
Like this? I know it's exaggerated a little bit, but like that? In the green? Not drawn to scale. Now please tell me, does this, I know I had this a little bit longer than I should have. Does this piece here look like it might be this piece in the original, taken across the y-axis? This piece here, reflected across the y-axis, might give me something like this. And might this little piece, which is more reasonable on this one, this little piece here that was on the original, taken across the y-axis, might give me the green here, on the other side. So is that graph reflected through the y-axis? Guys, does that answer your question with the negative sign there?
Yeah, for sure.
Now I know what you want. You're never going to get today though. You want, Professor, come on now. We're moving into math 7. Now put the 2x back in. I'm not going to do that right now, but can someone tell me, what would that require me to do? I've already done the negative. What, in addition to the same graph, would I have to do now to show the other part, which is now, I'm going to shrink the graph by what? 1 over 2, 1 over c, they say? That means go through what? Multiply the x coordinates by 1/2 on the graph? Is that true?
Yes.
On this graph that I have right now in the green? So pick up the green graph, multiply the x coordinates by 1/2, and see what happens there, and you get a final graph. Wow. I think, guys, we've done enough, I think, check my time here, on transformations at this point. Whew. Billy, on the handout, was that all I gave you for transformations on the handout?
Yes.
Okay. What happens next? Are we on the back?
Yes.
Are you kidding? Now, am I gonna go back and recap some of this probably on Wednesday? Of course I am. But I want you guys to sort of get in your mind right now some of those transformations. Now, am I kidding? What am I kidding about? Section 1.6. After all this, your textbook starts or stops with on 1.6 application problems. Now, back in school somewhere, your teacher may have called these word problems. And they can be difficult. Now, before I jump into a few of these and have a student read for us, try to make some sense of the word problems, we'll be finished with chapter 1, which I'm hoping we can get tonight. Now, I sent out tonight, earlier today, and some of you guys may have seen it in your email. I sent out the notes that my TA during the winter session took on sections 1.4 and 1.5. Is this section 1.5 the word problems or 1.6?
1.6.
Oh, 1.6. And I sent out what she did for me when she was my TA during winter. You see, she was on vacation, so I had she was on vacation, so I had a different TA. I still have Mr. Parker, I had another TA. I want you guys look at her notes, the one from the winter session, especially on what's coming up, what I'm gonna be doing. She graphed those piecewise functions that we graphed up here. Look, you've gotta look, check your email, check and see how she showed you these piecewise functions. And she wrote you little notes on the side there. And then these word problems coming up, wait till you see what she did there. Her sketches were much better than mine. To make some sense of these word problems. So I'm gonna go ahead and get 1.6 started. We may not get all of it finished. I'm checking my time here. Now, before I jump into it, I would assume that you get a good sense of this class is critical. Now, the state of California, right now, is asking all community colleges, us, every other community college in the state, not to offer this course any longer. They want us, when you first come in, you have no choice, you go to calculus. Math 7. There would be no Math 2. By the way, at this point, do we still have Math 3 and Math 4? Are those still listed as courses?
Yeah.
They are?
Yeah.
Are Math 3 and Math 4 still listed? Yeah. Those are not going away. So the state says if a student comes into your community college, Ramsey, any community college in the state, the first math course they're going to take is calculus. Now, can you guys imagine jumping into a calc course without having pre-calc? So a lot of us raised havoc with the state. They're a little angry now at us. They said, well, Santa Monica, if you create another course that might meet what we want, we can offer it rather than Math 2. Well, that's difficult. How are they going to replace Math 2? How are they going to replace me? Get real. Jeez. Oh, so it looks like they're going to keep Math 2 for a while, but they're threatening to do away with it. Do away with it. And when you come in, good luck. Students are coming in, they're going to be entered, no question, calculus. Calculus. Now, what are they doing with the calc course? They're doing something like they're doing this with this Math 2. Some of the courses will be Math 7 with a C after it, like we now have Math 2C for some courses. That's called a co-rec course. That means you have the same course I'm teaching right here, but you have added time with your instructor. So in other words, it's longer. Would you like to see Ramsey live more hours? Of course you would. So if I taught Math 2C, you'd see me more hours. No, we're just doing it math 2. You guys just get to see me twice a week. Math 2C, you probably see me 4 times a week. Now they want to do that same thing with calculus. They want to do a Math 7C just to make sure students coming in, they may need that little extra time, since that's going to be their initial course. Yes?
What's the state's reasoning?
What's their rationale?
Yeah.
Why on earth, we don't know yet. They give us reasons. They say they collect data. They look at the data, statewide, and look at the scores, and how many students pass Math 2, how many students pass Math 7, and they start doing a comparison. But do we really need Math 2? Because it looks like the number of students passing Math 2 may be enough to say they should have been in Math 7. Or on the other hand, maybe Math 7 scores are not looking good, and maybe that might be a rationale to keep Math 2 for a while. So guys, looks like right now at this point, I'm teaching summer. I'm teaching this same class during the summer. It's good for the summer. And looks like the fall schedule has not come out yet, so we don't know what's going to happen in the fall. We're hoping at least they'll offer some Math 2. Maybe not as many sections, but some. So that is what's happening now. Thank goodness you're now doing this while it's available before you go into a Math 7 course. Because I've taught Math 7 before, and I'm telling you, you would expect all this that we've done in the time you've known me. I would assume just walking in, you know that. And I'm going to start right off with limits. Calculus. Mr. Park, Isuja, did you guys start out with limits in your Math 7 course? For the first day. The instructor may smile, say hello, then say limits. You say, what? I've reached my limit. What are you talking about, limits? Jeez, and they see limits, and they're going to start limits. So guys, just thank goodness you're with me. We're doing the course. This is going to get you ready for that calc course. Now what I want to do, not too many tonight, I'm going to just do a couple of these application problems. And like I said, Wednesday I'll do a recap on this. Billy, I know you've been reading for me. If you don't mind, or I could ask another student, could you read the first word problem, and let's try to make some sense of it, on the applications.
Says, an open box with a square base is to be made from a square piece of cardboard, 24 inches on the side by cutting out a square from each corner and turning up the sides. Express the volume of the box as a function of length x of the side of the square cut out from each corner.
Now this sort of scares me. This sounds more like what you probably experienced somewhere, more like a math problem to deal with. It's in words. It didn't say solve. It didn't say find the domain. She's giving me something in words. And to make sense of the words first, and then try to answer the question there. Billy, if you don't mind, read for me one more time. Hang on just 1 second here so I can get ready for this. I'm gonna try something here. Read to me one more time.
An open box with a square base is to be made from a square piece of cardboard, 24 inches on the side by cutting out a square from each corner and turning up the sides.
Hang on. Now, she's telling me, Professor, we're supposed to have I think you said a square piece of cardboard? I think. My marker will work here. Let's say it looks something like this, and I'm going to illustrate also another way to look at this. He says, please take a square piece and do this to it. Square piece of cardboard. Did they tell me the dimensions, length and width of it?
24 inches on the side.
Oh, 24 inches on each side. It's a square. 24 inches. I'll put 24 inches down here. Should be 24 inches on all four sides. She says, take that, Professor, and do what to it?
Cut out a square from each corner.
Go to each corner and cut out a little square. Let's see if now we can do it like this. So go to this corner, cut out a tiny square. Mr. Park, Susan, when I finally get this look reasonable, squares, by the way, guys, are supposed to be the same size. Mine's not looking too good. And here. And I think you said those little pieces, being cut out squares. That. So here, X is X for the dimensions of the piece being cut out. Same size squares being cut out of the corners. And then, Billy, what they say after I take the pair of scissors and I cut out those little squares?
Express the volume of the box as a function of length X.
They're saying I'm supposed to be able to form a box. Now here's my FedEx. I told you guys about FedEx. Here's my receipt from this morning. Jeez. Okay, this is not a square, but let's assume it is. This is the piece of cardboard we're talking about. She's telling me, Professor, they want you to go to each corner, even on this rough sketch, and cut out, now this will be rough, but let me illustrate. Cut out a square on each corner, especially the same size squares. This will be enough to illustrate it. And do this. So far, so good. Each corner. Up here, this corner, same size square. Please cut it out. And here, same thing. And she says, Professor, after you do that, boy, I did it. They're saying, please fold up the flaps that are remaining. And is it possible, as I fold up the remaining sides, is it possible when I cut out, is it possible to form a box? And she says it's going to be open at the top. Guys, even with this rough sketch, is it possible? If I go through and do what she suggested, is it possible to form a box? Well, they're asking me about this box. Express its what? Volume. They're saying how much water, for example, could you pour in here? If you form the box, how much water could you pour into this, expressed in terms of volume? Now, back to my illustration. She says, Professor, what you're doing there, show, you already got the piece there started, now show this, that you have a box formed. And guys, let's make the box look something like this. I'm going to exaggerate it just to make it look better. Let's say the box looks like this. And here. So I can look at this and make some sense of it. And this. You see, Jim, Mr. Park, when I finally get this drawn the way I want it. Now we'll connect. And guys, there's something like this to look at. Now, he might exaggerate this so I can get some room to work. They're saying, from the box. Let's say the box looks like that. From doing this. Is that box pretty good? I think it's great. That looks good. Now, can anyone tell me how does one first express the volume? How much water can be poured into that? How does one find the volume of a box to begin with? Now, by the way, I think you said it's open at the top.
Yeah.
So it's open at the top, so they're saying, please, you're going to pour water into it. They want to express the volume. Does anyone think they know how to find the standard volume of a box? I see a hand going up. Go for it.
Length times width times height.
Very good. Length times width times height. Multiply the length times the width times the height. Now, here's my length. Guys, I think the length, and it came from me doing this, be careful. I think you gave me originally, Billy, remind me, was it 24 inches for the original down here?
Yeah.
Beautiful. And then I did this business here to it, and now I go here. Can anyone tell me a good way to express now the length of the box based on original 24 cut short on each side? I saw a hand going up.
I think it's 12.
I know why you said that. Yes.
24 minus 2x.
24 subtract 2x. Why 2x? Because you cut an x out here on that corner, and you cut another x out, understood to be there, on that side. Is that true? So the original was 24, but each corner you cut out an x. So 24 subtract 2x, beautiful. Now hang on, I got to get this off. The width, this is the width. Guys, that came from this. That's the width of the original cardboard. Has it also been cut short? How much? An x here and an x here. So can I use the same representation? 24 subtract 2x here. Now, the formula that's given to me, volume. You've got to multiply the length and the width and the height. Well, I have the length and the width. I don't have the height. Now, hang on. If I can find it here. Here it is. Even on this rough sketch, we got the length, width. Can anyone tell me, based even on this little rough sketch here, what might be the height? Because this little piece right here. What might be the height of that box?
Just that.
Represent that. Is that the X?
Yeah.
Is the height of the box just that mirrored piece right there? The height X. So here, I now know based on that, the height is X. Billy, read that to me one more time.
The entire thing?
Who read this? Yeah.
You wanna read, you want me to
Read the whole thing.
Okay. An open box with a square base is to be made from a square piece of cardboard, 24 inches on the side by cutting out a square from each corner and turning up the sides. Express the volume of the box as a function of length x of the side of the square cut out from each corner.
Ah, they're saying express the volume, length times width times height, but express it only in terms of X. The little X that represents the side of those corners. Guys, so they want you to find, yeah, they're going to use that formula. They want you to find V of X. Oh, just like F of X. G of X. They want the final answer only in terms of X. Well, let's see what happens here. Go back. The length, well, the length is 24 subtract 2x. Easy put in. The width, this little piece here, 24 subtract 2x. The height, x. Please tell me, is that all in terms of x?
Yeah.
That's what they wanted. They wanted this all expressed in terms of x. So v of x, the volume with reference to x. I'm gonna write it like this, guys. I think it looks better. I'm not going to expand this thing out. I think it looks better like that. X times 24 subtract 2x squared. And I would accept that as your expression for the volume of that box. Before I leave it. That's the answer. Billy, did they ask you to do anything else with it?
No.
Oh. Just express the formula, I did, in terms of x. Now, if it's a function, which it is, f of x, what do I usually, or the textbook usually ask you, when you deal with functions, they usually ask you to do something else with it. What do they ask you to do besides just the function? I notice they did not ask you to do it here. I'm asking you to do it though. Domain. Let's get, especially the domain. Let's get the domain out of the way. Now, what is the domain, the set of x's, that I am allowed to use here? See, hang on up, yes.
Any number greater than 0.
I'll take, now by the way, you see the side here? She said, Professor, you've got to definitely consider x is greater than 0. It's a length. We don't deal with negative lengths. That true? Now, besides that, though, I see something else I'd better consider. Besides x is greater than 0, let me step back and look at it.
That's 224.
Yeah, there's some other restrictions with what I'm hearing. What was it? Oh, not quite. I think I heard 24 in there.
12. X is less than 12.
Okay, you're saying x is less than 12. So are you saying the final domain might be from 0 up to 12, and that's it, the max? How can I find that? Because this side, length, this width, they also must be what? Greater than 0. Please tell me, is that true? 24 subtract 2x must be greater than 0. It's a length, it's positive. Let me go ahead and solve this inequality. What a nice problem here. Divide by -2, reverse my symbol. Is that x is less than 6? Or less 24? Yeah, that's not. Is that x is less than 12? I think. Is that true, guys?
Yes.
Now, what's my final domain? Let's put it in interval notation. Based on what you see, what would you write in interval notation for your domain?
0 to...
Okay, 0 included or not?
No.
No. Open, 0 up to
12.
12. May I use 12?
No.
No. That's your domain. From 0 up to 12, not including 0 or 12. Now suppose you got outside that interval. Well, something should happen. It shouldn't work. So we try 13. I'm not saying just try numbers between 0 and 12, and not even the 0 or 12 can be used. We'll try 13. What would happen if I take 13 back? Well, some big things would happen here. This side's okay, that's 13, right? This down here would be 24 subtract 2 times 13. That would be 24 subtract 26.
Yeah.
Negative. You can't have a negative word length. So I could use 13. Anything caught between 0 and 12, guarantee you, will work. Will make sense for us. But if you get outside that interval, it's going to mess up the sides there. You're going to get a negative answer for the length of the side. How's that look? Okay? Billy, I'm looking at my time here, and I know you guys are definitely looking at the time. Oh, yeah. I've always said I might do this on your quiz. At what time does class end? And I guarantee you, every student in class will say 7:45. Is it 7:45? We wish. It's what, 7:25? Yeah, so if I gave you that just on the side for a little extra credit point, we get that? Every student gets 725. But if I ask you to draw a box and find its volume, different issue. Different issue altogether. Guys, this one's done. This is all they asked me to do. Now, when you reach calculus, because this is probably the last one I'll do tonight, Susan, Mr. Park, did you guys have something like a box in calculus to deal with? Remind me, did you have a box of some sort in your calc course? I know you two guys had different instructors. A box of some sort where they ask you to maximize the volume? Find the most water, what's the highest amount of water can be poured in before it starts overflowing? You did something like that? So they may ask you to maximize, where is it? This. Which for us means to find the maximum. Which for us might mean to find the local max. Or an absolute max. May require us to graph that. And see where the local max or the absolute max is. To answer that question in calculus. At least you'll remember from this class what it looks like, the box. Guys, it's almost time for me to close down. Susan, we've had a beautiful class. I'm not finished yet. Jeez, you know me. Mr. Park, you guys have anything to say? Now, Susan, she's leaving us. I hate to see her go. I've been with her so long here, I just hate to see her go. And she has not quite decided which school she wants to go to yet, right? But she's going off to the university, some university. And I've written her a few recommendations. What is your choice school? Where would you really like to go?
I wanna go to DuPenn
University of Pennsylvania, okay.
or Columbia.
Oh, Columbia, I wrote your recommendation for Columbia.
I was accepted to UC Berkeley, so maybe. But as a like out of high school though.
UC Berkeley's already accepted you.
But it was like out of high school, but I ended up here. I didn't go.
You didn't go to Berkeley. She came to us, SMC. I'm so glad she did. So glad she did. But she's leaving us. So I have to get a replacement for her for my next class, master class. Mr. Park, you're gonna be with me though.
Yeah, I want to stick with you till next summer.
He's gonna stay with me for the summer and probably the fall also.
Next year summer.
Next year.
Next year summer.
Hopefully they don't take the course away from us. Okay, so hopefully we'll be together. Guys, you think what I should do? We got how many minutes left? Very few. Okay, Mr. Park, Susan, have sent some of you guys out an email. Check your email to see what they have planned. They call it a study buddy program, where they're going to be so available. They're just right there for you, right, guys?
Mm-hmm.
When you need them. We tried that in another semester, and it really, really helped. So if you contact them, and they're going to be there for you, and I'm here for you during my 4 o'clock session, and they're going to be with you now also. You guys look at that email and see what they want you to do. Something else I was going to mention. What else was it? I'll read it tonight. Yeah, I thought something else I was going to add to this. I had a nephew who just graduated NYU, New York. This kid did his graduated valedictorian of his school. About 300 students at that school or whatever, he was number one. So he goes off to NYU. NYU is very expensive. So his parents, and his uncle, we all had to bear the expense. I got tired of it. I was going to just drop him. I just take all my money. But we all got through. Then he gets finished, and he decides, no, I want to change my major. What? And I want to stay longer in New York. I don't know whether he just liked New York. He's right in the city. like New York City and maybe like that. And we thought, what? What the hell, did you get through the years? You took my money, me especially, I didn't want to complain anyway, where's my money?